These are the answers to the notes on chemical equilibrium for Unit 8. At any point when you get through this, you're probably going to need to stop the tape, or stop the video and actually write some things out on your notes. It will be extremely helpful to you if you do that. Write everything out. Don't just copy what I have or ignore it. You'll find that doing the problems will be significantly easier if you've actually taken the time to write things out. All right, our first question. What are the two opposing processes involved in this figure, and what are their relative rates in a saturated solution? Well, our two processes are solvation and crystallization. And this is where we have solid sodium chloride, which turns into aqueous sodium ion and aqueous chloride ion. And we're going to define chemical equilibrium. And this occurs when opposing reactions proceed at equal rates and the concentrations of reactants and products don't change over time. They stay constant. Now, we're going to talk about the concept of equilibrium. And first thing we're going to do is tackle this relationship here. N2O4 gas goes to 2NO2, which is also a gas. Now, question A asks us to consider the reaction shown above. What is the most obvious sign that this reaction involves some sort of equilibrium? And that would be the use of double or double-headed arrows. There's a variety of ways to write this. You'll see a number of different ways depending on books and questions that I give you. What are the colors, if any, of each of the following substances? Well, for N2O4, that will be colorless, and for NO2, that will be a brown gas. All right, the tube in figure 15.1 starts out as colorless in appearance. What chemical is present in the tube at the beginning? Well, that will be, of course, dinitrogen tetroxide, N2O4. And as this reaction progresses, the appearance of the tube gets darker. What's happening at the molecular level to explain why it's getting darker? Well, the answer is that N2O4 is decomposing to form NO2. At some point, the color in the tube stops changing. The student decides that the reason that the color stops changing is because the reaction is over, and all of the N2O4 molecules have been converted into NO2 molecules. Do you agree or disagree? And explain your answer. Well, I disagree, and my reasoning is that the backwards reaction is occurring at the same rate as the forwards reaction. And at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. The equilibrium mixture results because the reaction is reversible. N2O4 can form NO2, and NO2 can form N2O4. And we write the equation for the reaction with two half arrows pointed in opposite directions. Or we could use a double-headed arrow. Okay? We're going to learn more about rates when we study kinetics, but right now we can say that the rate of the disappearance of N2O4 is linearly proportional to the amount remaining. And we write this as this way. We say the rate forward is equal to some constant, some forward constant, times the concentration of N2O4, where square brackets indicate molarity or some sort of concentration units. And then we write the reverse reaction as the reverse rate is equal to some K reverse times NO2 squared, where Kf and Kr are the rate constants for the forward and reverse reactions. In a minute, we're going to talk about where these expressions come from. Right now, just be patient. At equilibrium, the rate at which NO2 forms in the forward reaction equals the rate at which N2O4 forms in the reverse reaction. And if that's true, then we set these two expressions equal to each other. And I can rearrange this to get NO2 squared over N2O4 is equal to Kf divided by Kr. And since I have a quotient of two constants, that is itself a constant. And we call this constant the equilibrium constant. Okay, once equilibrium has been established for a chemical reaction in a closed system, the concentration of the reactants and the products no longer changes over time. However, this does not mean that the reactants and the products stop reacting. It's a dynamic process, and that means that some reactants are being converted into products and vice versa. Some products are being converted back into reactants. So we consider a general reaction that looks like this. A reacts and turns into B in some sort of equilibrium state. We want to classify the following statements as true or false. All right, the first one, once equilibrium is established, the concentration of A is equal to the concentration of B. Well, that is simply false. That's not the definition of equilibrium. Once equilibrium is established, the forward rate is equal to the reverse rate. And that is a true statement. That is the definition of equilibrium. Once equilibrium is established, the values of A and B are no longer changing. Well, that is a true statement. That's the definition. Once equilibrium is established, A and B are no longer reacting. I think we can see that that is a false statement. Once equilibrium is established, the ratio of B divided by A equals 1. Well, that's also false. Now, the ratio of B divided by A is a constant, but it isn't necessarily equal to 1. And of course, I've just given away the answer to the last one. Once the equilibrium is established, the ratio of B divided by A equals a constant. Yes, that is a true statement. All right, we look at the next section, which in your notes is labeled section 15.2, because in the book from which these notes come from, that's section 15.2. So we've got the Haber process, a very important industrial application. This is where nitrogen plus hydrogen reacts to form ammonia. This was very important at the beginning of World War I in Germany. And it was a very well-known, well-documented process in the German chemical industry. Now, it's a reaction in which nitrogen gas and hydrogen gas react to produce ammonia. And we're going to monitor the concentration of all three substances over time in a closed system. And we get the following two diagrams from two separate experiments. So we see experiment 1 and experiment 2, and they certainly do look different in terms of the initial concentration of hydrogen and the initial concentration of ammonia. So we have a couple of questions. On each graph, we want to draw a vertical line to indicate the time at which equilibrium has been achieved. And the second question is, how are experiments 1 and 2 similar? How are they different? Well, here's our two vertical lines to indicate the time at which equilibrium has been achieved. The concentrations of all the reactants and the products is no longer changing with respect to time. And we see that the red line is about that time where that's occurred. And then how are these experiments similar and different? Experiment 1 starts with only reactants, okay, N2 and H2. Experiment 2 starts with only product. Both experiments end with the same concentrations of all three chemicals, but all the concentrations are different. Okay, when equilibrium has been achieved, is it true that the concentration of nitrogen is equal to the concentration of hydrogen, which is equal to the concentration of ammonia? Well, one look at these diagrams shows us the answer is no. Now, we want to write an equilibrium constant equation from page 514. This is page 514 in our book, our Zumdahl and DeCoste book, which deals with the law of mass action. This is very important, and this is where the conditions of equilibrium come from. We're going to use this largely through the rest of the semester. For the reaction AA plus BB reacts to form CC plus DD, where capital letters A, B, C, and D are the individual molecular or ionic compounds involved, and the lowercase letters A, B, C, and D are the stoichiometric coefficients, we can write an equilibrium expression, and it looks like this. We can say that the equilibrium constant is equal to the concentration of each of the products raised to their stoichiometric coefficients divided by the product of the reactants, however many there happen to be, each raised to their stoichiometric coefficients. Now we call this relationship the equilibrium expression for the reaction. The constant K sub C is the equilibrium constant. In German, the word constant is spelled with a K, which is where this comes from. And it's the numerical value we get when we substitute the molar equilibrium concentrations into the equilibrium expression. So we want to write the equilibrium constant expression for each of the following reactions. The Haber process. And we look back at the Haber process where we have nitrogen plus 3 hydrogens react to form 2 ammonias. So we write our equilibrium expression. We say that that's equal to the products raised to their stoichiometric coefficients. In our case, we have only one, ammonia, divided by the reactants, each raised to their stoichiometric coefficients. The stoichiometric coefficient for nitrogen is 1 and for hydrogen 3. So we get this relationship. Question or subpart 2 here, the reaction that involves the decomposition of hydrogen iodide into its elements. Well, here's my reaction. 2HI reacts to form I2 plus H2. So I can write an equilibrium expression because here I have Kc is equal to, and then I take again each of the products raised to its stoichiometric coefficients, which would be 1, divided by the reactants, in our case hydrogen iodide, squared because the stoichiometric coefficient is 2. Now on the next page, we're going to fill in the missing information for the change in concentration for each chemical, and we're going to use a minus or a plus sign for each value. We've got 5 experiments here. All right, experiment 1, we start with dinitrogen tetroxide reacting to form 2 nitrogen dioxides. My initial concentration of nitrogen dioxide is 10, and my equilibrium concentration is 9.3. So I can say that my change is a minus 0.7. And over on the other side, when I look at nitrogen dioxide, I see that my change is a positive 1.4. All right, let's look at experiment 2. I start with no nitrogen, no N2N4, and I have a final equilibrium concentration of 4.51. So I get positive 4.51. And on the right side for nitrogen dioxide, I can say that I have lost negative 9.02. And I go through all 5 of these experiments, simply subtracting the equilibrium concentration from the initial concentration to find my change. Sometimes this number is positive and sometimes it's negative. Negative signs mean mass is lost. Positive signs mean that mass, or in our case, the concentration, is gained. We can continue down the list and we can fill in all the numbers simply by subtraction. And I'm going to stop here and we'll proceed on our next page starting at the beginning of the next video.